I said earlier that stars were very far. The celestial sphere was very large, and left for later an investigation of, what do you mean by very large? How far are the stars? Well, in one sense it's later now, because we're about to understand what we can say, or what it was that Aristotle knew about the distances to stars, or how large we need to make the celestial sphere. In another sense, it will be later for the next few weeks, because as we'll see, the effort to measure the distances to things in the heavens will be a central thrust of the effort to understand what it is that these things are that we see out there. So our understanding of the nature of astronomical objects will be intimately tied with efforts to figure out how far they are. As we go along, we will learn that humans have recruited into this effort a huge array of techniques and technologies for figuring out the distances to astronomical objects. Let's start at the beginning, and the beginning is direct geometry. We can make a measurement of the distance to objects in the sky under some circumstances. The technology we use is called the small angle approximation. Let's see what the geometry is, and then we'll see how we use it in astronomy. So, as I said, this deals with the relation between angles and distances, so we're going to build a triangle. And we're going to denote two of the vertices of our triangle by A and B and one by O, and the distinction is going to be, we're going to work with specific triangles in which one of the sides of the triangle, the one I denote by D, is much shorter than both of the other sides. It's so much shorter that I can assume, for all intents and purposes, that A and B are equidistant from O. How can I assume that? Because if D is much smaller than the distance R from O to either A or B, then the difference between the OA distance and the OB distance, which is at most D, is negligible compared to R. Does that hold in this triangle? Well, this brings us to the question. What do we mean by very small? In this triangle, I would estimate that D over R is about a third. What that means is that if we use the small angle approximation, any calculation we make might be setting to zero or omitting things that are of order D over R, and so our answers might be off to by about 30% of what we want them to be. If you want the small angle approximation to be more precise, perhaps you wish to work in a triangle like this one, in which D over R is of the order of a tenth, and the small angle approximation might be good to about 10% accuracy. In many of our triangles, D over R will be a millionth, and the small angle approximation will be even better. So let's erase all my scribbles and see what the small angle approximation allows us to actually compute. So, let's introduce the eponymous small angle. The angle that is small when D is much smaller than R is, of course, the angle at the vertex O. I will call that angle alpha. And trigonometry allows us to construct a relation between R, D, and alpha, but we won't need trigonometry. If D is much smaller than R, we can make the following calculation that simplifies that relation to something that is easier both to understand and to remember and does not require trigonometry. So I'm going to construct an auxiliary geometric object here. I'm going to draw a great big circle around O, centered on O, with radius R. And by my assumption, that means it goes through the points A as well as the point B. And I'm going to try to imagine that instead of trying to figure out the length D of the interval between A and B, I want to figure out the length of this arc, the part of the circle lying between A and B. Well, that's denoted by AB with a little squiggle on top, reminding me that it's the arc length. If you imagine that the circle is a pie and the green line is the crust, and you want to know how much crust you get when you take this slice of pie, along with this slice of pie comes a fraction, alpha out of 360 degrees of the pie, and you get the corresponding fraction of the crust. The length of the entire crust is the circumference of the circle, which is 2 pi r. And we combine this into this fancy, well-written relation. This, of course, holds without any approximation. It's an exact relation whether you're getting a small slice of pie or a large slice. What is true when you get a small slice is that if the slice is sufficiently small, if the angle alpha is a small angle, if D is much smaller than R, then the difference between the arc length that we computed and the actual straight line distance between A and B is very small. So in the small angle approximation, d, which is the straight line distance between A and B, is approximately the same as this arc length that we've computed. This is what the small angle approximation buys us. Now, again, what does that explicitly mean? What it means is that this is true to within errors of the order of d over r. So in our case, I would say that the difference between the arc length and the straight line length is no more than a third of either of those two lengths. This is the small angle approximation, so let's bring that in. The small angle approximation allows me to approximate the distance d by the arc length that we computed AB, and computing the math here, dividing 360 degrees by 2 pi, I can write that in this fancy formula. This is the small angle approximation. Draw a box around it and remember it. It tells us that d, the distance between A and B, is related to r by and to the angle that they subtend, we say, at O by this relation. Now, in astronomy, we will build such triangles in several ways. So what realization of this did I have in mind? Well, when I was talking about the celestial sphere, I actually had the following idea in mind. I had in mind that O, in fact, was some distant star, some point along the celestial sphere. A and B, on the other hand, were two different points from which we can view the celestial sphere. Where do we get to view the celestial sphere from? Say, Athens and Rhodes. 2 points on Earth. And so the distance in the context that I was thinking about, d, was of the order of the size of the Earth. At most, the radius of the Earth, which we will denote this way, is about 6,400 kilometers. And r is, r is the distance to a star, and in our approximation, it's the radius of the celestial sphere. So, is the radius of the celestial sphere much larger than the radius of Earth? That's the question we're asking in this case, and the answer is yes. How do we know? Well, because we can measure the angle alpha, the angle made by the line from one point A on Earth to a star and a different point on Earth to the same star. If those angles are different, what that means is we actually obtain a different view of the sky from the point A and B from two different points on Earth. We call this angle in that context the parallax angle. We are now measuring the distance to stars in the same way that we estimate distances to things by observing them through our two eyes and comparing the two images. And what Aristotle is well aware, is that the sky looks almost exactly, and to within the precision of his measurement, exactly the same as viewed from different points on Earth. This parallax angle between 2 points on Earth and a star has in fact not been measured. It's very, very small. So that tells us that indeed the celestial sphere is so large that we can assume to any precision that we can measure this angle alpha to be 0. Stars are indeed very much farther from Earth than is the size of Earth. And now this is what I meant by saying the celestial sphere is very large. Saying that it is very large is a meaningless statement. To say that some physical quantity is large is meaningless until you say large compared to what? The radius of the celestial sphere is much larger than the Earth's radius. We've settled the question of the size of the celestial sphere, but the small angle approximation will go with us. So as I promised, we are in no way done with estimating the distances to stars, but our first attempt to measure the distance is, if you want, a failure. We measure that the distance is so large that we can't actually measure it. So it's larger than any distance we can compute. We may as well assume it to be very, very large. That's what we've done. Now, the angles that we measure in the context of astronomy are often going to be very small, and measuring them in degrees will be inconvenient, so we often will have recourse to smaller measures of angle. We will actually follow the ancient Babylonians and subdivide a degree to 60 into 60 arc minutes, and each arc minute into 60 arc seconds. And so a angle of 1 degree will correspond to an angle of 3600 arc seconds. And since we typically measure very small angles, arc seconds will be a convenient unit in which to measure angles. And so one can then compute that this angle, to which I'm computing the ratio here of 57.3 degrees, or a 2π of 360 degrees, is equivalent, doing the math, to 57.3 times 3600. You find that the following is another equivalent way of writing the small angle approximation. The ratio between the short and long side of the triangle is given by the small angle divided by this angle. Notice that 206,265 arc seconds is just another way to write 57.3 degrees. This is the form in which we'll often use the small angle approximation, and this brings us to the last point I wanted to make, and I've sort of been hinting at it as we went along. We are going to be doing physical science. We're going to be discussing physical properties of the universe, like the distance to a star or the size of a galaxy, and we are going to be trying to mathematically and precisely describe these, and as Lord Kelvin taught us, to do that we need to assign them numbers. But what does that mean? So assign a number to, say, some important physical quantity such as my length. Well, depends who you ask. Some people will tell you that my length is about 167, and other people will tell you that my length is about 5.5, so who's right? Well, they're both, of course, right. The point is that assigning a number to the length of me is an irrelevant statement. What the number really tells you is how much longer I am, or how much shorter I am, than something else. The person who said I'm 167 is my length meant that I was 167 times longer than some standard they call a centimeter, and so on. We use units to detect what it is, what is the standard length, mass, whatever it is, to which I'm going to compare. This was very evident when we decided that we could measure angles in degrees or in arc minutes or in arc seconds, so that one person could describe an angle as 3 degrees, another person would describe that very same angle as 180 arc minutes, and a more ambitious person would measure that same angle in arc seconds. But I can't do that calculation in my head, so I won't put that down. So the number that you assign to, for example, an angle is meaningless until you say, in what units are you measuring that angle? In what units are you measuring that distance? Making sure that when you assign a number to a physical quantity, you remember what units you are measuring, what ratio it is that that number designates, is going to be very important as we go along. So, in particular, when we derive or find all kinds of mathematical relations between physical quantities, for example, we found in the previous slide that d was equal to alpha divided by 206,265 arc seconds times r. Well, now, this is a relation, as an equality. It's an equality of two numbers. Thought of physically, it relates this distance to that distance. But clearly, say this distance is the same as that distance, means that they will correspond to the same numbers if you measure them in the same units. Now, in particular, the distance between A and B, remember D was the distance between our points A and B, and R was the length of the long side of the triangle. If I measure this in millimeters and this in light years, this relation will not be true, despite the fact that it's a correct relation between the distances. It will not be the relation between the numbers we associate to them. This will only hold if I measure D and R in the same units. What's the easiest way to assure that all of our equations are valid in whatever units we use them? Well, one easy way to do it is to write this equation in an equivalent but simpler way. Write it this way. This way, we see that on the left-hand side, we're writing the ratio of d over r, d to r. That's the ratio of two distances. That is actually a meaningful number. So that is the ratio of d in meters to r in meters, or d in light years to r in light years. And as long as we use the same units to measure d and r, it's true whatever units we use. Likewise, the right-hand side is the ratio of two angles, the angle alpha and the angle 206,265 arc seconds. The ratio of those two angles is a number, and so our equations are now relating to numbers. And whenever you can write your equations completely in terms of ratios, you will find that you will not have issues with unit conversions, and you will spend some of the time in this class converting the units on various calculations and making sure you're measuring everything in the right units. So consider this to have been your warning about this.